Good day, everyone.
I'm gonna introduce the members of Group 4.
First is Ryan Ayasays.
Second is Malvin Ayup. Third is Jamal Requiem. Fourth is Jovi Pasigad.
Hello everyone, I'm Ryan Asas. I'll be presenting to you the gas turbine power plant. A gas turbine is also called a combustion turbine. Is a type of internal combustion engine. It has an upstream rotating compressor coupled to a downstream rotating turbine and in between a combustion chamber. The basic operation of a gas turbine is similar to that of a steam power plant, except that air is used instead of water. A generating station which employs a gas turbine as the prime mover for the generation of electrical energy is known as a gas turbine power plant. Here's a schematic diagram of a gas turbine. Ang air na to is usa siya ka dong sa compressor is magisa siya og filter kay para ma-filter out ang mga impurities para hinlo siya iniabotan sa atong compressor. Then ang atong na-compress na air is atong dalon ara sa combustion engine or combustion chamber. Heat is added to the compressed air either by burning fuel in the chamber or by use of air heaters. The hot and high pressure air from the combustion chamber is then passed to the gas turbine, where it expands and does the mechanical work. The gas turbine drives the alternator, which converts mechanical energy into electrical energy. Gas turbine is usually started by an electric, hydraulic, or pneumatic starter motor. It's coupled via the usual power take-off and gearbox to the shaft of the gas turbine. So, before mo start ni ato ang gas turbine is kinahanglan mo na siya og external force para muandar atong compressor. Then, once na muandar na siya is automatic na siya, din na siya magkinahanglan sa ato ang kanatong starting motor. Here's a short video about gas turbine.
Air. A lot of gaseous molecules floating all around us. It's great for breathing, and it turns out it's great for getting lights turned on. That's because air, along with abundant natural gas or other fuels, are the ingredients that combine in a gas turbine to spin the generator that produces electric current. If you follow the electricity you use at home or at work back through the power lines to your local power plant, you'll see that the process most likely starts with the work of the gas turbine, the very heart of the power plant. First, air is drawn in through one end of the turbine. In the compressor section of the turbine, all those air molecules are squeezed together, similar to a bicycle pump squeezing air into a tire. As the air is squeezed, it gets hotter and the pressure increases. Next, fuel is injected into the combustor where it mixes with the hot compressed air and is burned. This is chemical energy at work. Essentially, this is what happens in your family car's engine, but at about 2,900 times more power. Actually, it's exactly like the turbine engines on jet airplanes. The hot gas created from the ignited mixture moves through the turbine blades, forcing them to spin at more than 3,000 RPMs. Chemical energy has now been converted into mechanical energy. The turbine then captures energy from the expanding gas, which causes the drive shaft, which is connected to the generator, to rotate. That generator has a large magnet surrounded by coils of copper wire. When that magnet gets rotating fast, it creates a powerful magnetic field that lines up electrons around the coils and causes them to move. The rotating mechanical energy has now been converted into electrical energy, because the movement of electrons through a wire is electricity. In what's called a combined cycle power plant, the gas turbine can be used in combination with a steam turbine to generate 50% more power. The hot exhaust generated from the gas turbine is used to create steam in a boiler, which then spins the steam turbine blades with their own drive shaft that turns the generator. What you end up with is the most efficient system for converting fuel into energy. And that's your GE Gas Turbine 101.
Here are some examples of different kinds of gas turbine in the gas turbine power plant in the Philippines. First is Santa Rita Combined Cycle Natural Gas Fired Power Plant. First Gas Power Corporation or FGPC. The Santa Rita plant is a 1,000 megawatt combined cycle natural gas fired power plant located in the First Gen Clean Energy Complex in Batangas City. Its operation commenced in August 2000. It used Santa Rita Combined Cycle Natural Gas Power Plant uses natural gas from Malampaya gas field in offshore northwest Palawan and can also utilize condensate, distillate, and naphtha as backup fuel. Next is the San Lorenzo Combined Cycle Natural Gas Fired Power Plant. San Lorenzo plant is a 500 megawatt combined cycle natural gas fired power plant that is located west of and adjacent to the Santa Rita plant. The plant commenced commercial operations in October 2002. Next is the Avion Open Cycle Natural Gas Fired Power Plant. The 97 megawatt Avion Open Cycle Natural Gas Fired Power Plant, which started commercial operations on September 26, 2016, was developed by First Gen's wholly owned Prime Meridian Power Gen Corporation or PMPC. The plant is located in the First Gen Clean Energy Complex in Batangas City. Avion uses 2 units of General Electric's LM6000 PC Sprint aeroderivative gas turbines, making it the first power plant in the Philippines to run on aircraft engines for land-based power generation application. Next is the San Gabriel Combined Cycle Natural Gas Fired Power Plant. A 420 megawatt San Gabriel power plant is the most efficient natural gas fired plant in the Philippines. San Gabriel started commercial operations on November 7, 2016 and is located in the First Gen Clean Energy Complex in Batangas City. San Gabriel utilizes Siemens SCC 6-8000H combined cycle gas turbine, which is designed to offer operational flexibility. The following are the major fields of application of gas turbine. First is aircraft field, second is electrical power generation, third is marine propulsion, and fourth is oil and gas industry. The aircraft field is by far the most important use of gas turbine is in aviation, where they provide the motive power for jet propulsion. In electrical power generation, even though the initial cost of a gas turbine is less than either alternative for moderately sized units, its inherent efficiency is also lower. Yet a gas turbine unit requires less space and it can be placed online within minutes, as opposed to a steam unit that requires many hours for startup. As a consequence, gas turbine engines have been widely used as medium-sized peak load plants to run intermittently during short duration of high power demand on an electric system. In this case, initial cost rather than fuel charges become the prime consideration. In marine propulsion, the propulsion demands of high-speed naval vessels often rely on gas turbines, producing significant amount of power, achieving thus high performance requirements. Gas turbines can be used either to provide purely mechanical propulsion or alternatively to generate electricity, which is subsequently used by electric drives to propel the ship. In oil and gas industry, gas turbines are used on oil platforms to make power. The oil platform is like a small city, isolated out on the water, so it requires a lot of power and does not have a lot of space. Gas turbines are also used in oil refineries to make power for the cracking process. Working principle of gas turbine power plant. Air is compressed, squeezed to a high pressure by a compressor. Then, fuel and compressed air are mixed in a combustion chamber and ignited. Hot gases are given off which spin the turbine wheels. Gas turbine burn fuels such as oil, natural gas, and pulverized or powdered coal. Gas turbines have three main parts. First is the air compressor, second is the combustion chamber, third is the turbine. Here's the figure of a gas turbine. Here is the compressor, the combustion chamber, and the turbine. What is a compressor? Compressor draws in air and compresses it. The compressor used in power plant is generally a rotatory type. The air at atmospheric pressure is drawn by a compressor via the filter which removes the dust from the air. The rotatory blades of the compressors push the air between stationary blades to raise its pressure. Thus, air at high pressure is available at the output of the compressor. There are two types of compressor: the radial or centrifugal flow compressor and the axial flow compressor. Radial or centrifugal flow compressor is used of the majority gas turbine and optimized for highest efficiency, but generally do not allow for portability and cannot handle severe environmental conditions. Consequently, ruggedness is often sacrificed for efficiency. While this may be desirable for most permanently installed large power plants application, it is not practical for small portable power generation applications. The advantage of radial centrifugal flow is as a simple design, good for low compression ratios of 5:1, while the disadvantage is that it is difficult to stage and is less efficient. While the axial flow is the air flows parallel to the axis of rotation. The compressor is composed of several rows of airfoil cascades. Some of the rows called rotors are connected to the central shaft and rotate at high speed. Other rows called stator are fixed and do not rotate. Axial flow is good for high compression ratios of 20:1 and it is most commonly used. Controlling load on compressor. To ensure maximum efficiency and allow for flexibility, compressor can be split into high pressure and low pressure sections. Vane control. In inlet vanes or nozzle, angles can be varied to control airflow. Compressor stall. The interruption of airflow due to the turbulence. Use of compressed air. Primary air, which is 30%, passes directly to the combustor for the combustion process. The secondary air, which is 65%, passes through the holes in perforated inner shells and mixes with combustion gases. The film cooling air, which is 5%, insulates or cools the turbine blades. The second part of the gas turbine power plant is the combustion chamber. In the combustion chamber, heat is added to the air by burning oil. The oil is injected through the burner into the chamber at high pressure to ensure atomization of oil and is thorough mixing with air. The result is that the chamber attains a very high temperature, about 3000 Fahrenheit. The combustion gases are suitably cooled to 1300 Fahrenheit to 1500 Fahrenheit and then delivered to the gas turbine. In combustion chamber, fuel is pumped in and ignited to burn with compressed air. and spark plug is used to ignite the fuel. There are three types of combustion chamber. First is can type combustion chamber, which is used for small and centrifugal compressors. Second is the annular, which is used for larger axial compressors, which such as LM2500. Third type is the can-annular type of combustion chamber for really large turbines. Can-type combustion chamber. Ang money figure sa to ang can-type combustion chamber. Then kini sa atong can-annular type combustion chamber. Then kini atong annular type combustion chamber. Ang kalahian din nilang tulo kay ang kaning si can-annular kay sa kaning ila sa kaning na mo siya ang can type kanina kani. Then nagpalibot sa sa to ang kaning engine. Then ang kaning si is nani si Jai kanang fuel injector, liner, casing o igniter. Kadakan ani niya. Then ang kaning si can annular pare-pareha ra sila ni can type pero ang kalahian nila is ang iyang igniter. Okay. Ang sa can type is individual, ang isahang kadakan is na igniter, pero sa kaning can annular is usa ra sila sa tibuok circumference ni za kanina tungod ani ni isahang kaning liner holes kani connected man na siya. So once may ignite is magdungan sila og ignite, pero tagsa-tagsa sila og kaning fuel injector, liner o casing. Ang kaning annular type combustion chamber is lahi siya kumpara sa can type o can annular. Kani is mo ni gigamit ron sa mga modern nga klase sa gas turbine. Ang iyahang is nausa ra ang iyahang casing wala si Jai kanang kankans giusar sa na kanina magpalibot na sumatay kalahian sa nilang tulo. Last part of the gas turbine is the turbine. The products of combustion consisting of a mixture of gases at high temperature and pressure are passed to the gas turbine. These gases in passing over the turbine blades expand and thus do the mechanical work. The temperature of the exhaust gases from the turbine is about 900 Fahrenheit. Application of gas turbine. It drives pumps, compressors, and high-speed cars, aircraft, and ships. Power generation, which is used for peak load and a standby unit. Open cycle gas turbine power plant and its characteristics. Open cycle gas turbine power plant and its characteristic. Gas turbines usually operate on an open cycle. Air at ambient condition is drawn into the compressor, where its temperature and pressure is raised. The high pressure air proceeds into the combustion chamber, where the fuel is burned at constant pressure. The high temperature gases then enter the turbine, where they expand to atmospheric pressure while producing power output. Some of the output power is used to drive the compressor. The exhaust gases leaving the turbine are thrown out, not recirculated, causing the cycle to be classified as an open cycle. Closed cycle gas turbine power plant and its characteristics. The compression and expansion process remain the same, but the combustion process is replaced by a constant pressure heat addition process from an external source. The exhaust process is replaced by a constant pressure heat rejection process to the ambient air. So, ang kalayan sa closed cycle o open cycle kay ang kaning atong closed cycle is magamit ni siya og working fluid such as air or any other suitable gas such as helium, argon, hydrogen, anion. Nga mabalik-balik na to sa ato ang cycle. Nga ang kani once nga kuan mo agi si ni sa kuan atong combustion chamber, this is mismo ang atong i-combust. Ang kuan lang is siya mo atong initon din mo atong pasa sa turbine, then pasa na po siya sa heat exchanger which is pa cool down na siya paubsan ng heat, kuha ng heat, then ipalik na po sa compressor, then balik-balik ang cycle. Gas turbine inlet air cooling JTAC is an example of na advanced technology nga gigamit karon sa mga gas turbine. Also known as turbine inlet air cooling or TIAC and turbine inlet cooling TIC. GTIAC is a cost-effective solution that meets the growing demand for power without adding more generators. This technology can increase a gas turbine generator's output to produce 30% plus more electricity at a fraction of the cost of a new gas turbine generator. How to minimize NOx emission in gas turbines? First is the water or steam injection. Second is dry low emission or DLE. Third is selective catalytic reduction or ACR. Water or steam injection, also referred to as weight control, which lowers the flame temperature of combustion reactions, which leads to nitrogen oxide or NOx production and in turn limits the output of NOx. Water or steam is introduced according to a specific water to fuel ratio, which depends on the fuel used to maximize cooling while making sure reactions still proceed as they should. One limitation of this method is that carbon monoxide and hydrocarbons released when weight controls are introduced. Each are dangerous chemicals for humans and considered pollutants. Dry low emission or DLE. An alternative to using water or steam was developed so that peak flame temperature could decrease. This approach to minimizing NOx emission in gas turbines adjusts several combustion conditions and it is called dry low emission. Selective catalytic reduction or ACR. In ACR equipped gas turbine, an ammonia reagent reacts with gas containing NOx to convert it into harmless nitrogen and water vapor gases. When combined with DLE strategies, nitrogen oxide emissions significantly lowers. Advantages of gas turbine power plant. Storage of fuel requires less area and handling is easy. The cost of maintenance is less. It is simple in construction. There is no need for boiler, condenser, and other accessories as in the case of steam power plants. It uses cheaper fuels such as kerosene, paraffin, benzene, and powdered coal can be used, which are cheaper than petrol and diesel. Gas turbine plants can be used in water scarcity areas. Less pollution and less water is required. Disadvantages of gas turbine power plant. 66% of the power developed is used to drive the compressor. Therefore, the gas turbine unit has a low thermal efficiency. The running speed of gas turbine is in the range of 4,000 to 100,000 rpm and the operating temperature is as high as 1,100 to 1,260 Celsius. For this reason, special metals and alloys have to be used for the various parts of the turbine. High frequency noise from the compressor is objectionable. Methods of improvement of thermal efficiency of open cycle gas turbine plant. First is the intercooling, second is the reheating, third is the regeneration. Intercooling. A compressor utilizes the major percentage of power developed by the gas turbine. The work required by the compressor can be reduced by compressing the air into two stages and incorporation of an intercooler between the two. So muna itong schematic diagram sa ito ang intercooling. Ang atong compressor is gibahin na duha ka section. First is the low pressure, then kaning isa is the high pressure. Sa una ani is kaning low pressure, which is kanang mag-compress sa air, then ang na-compress nga air is high na ang iyang temperature. Then para mas ma-compress pa nato ang iyang air is iagi nato og kaning cooling medium or kaning ato intercooler. Then once na mo ubos ng iyang temperature is i-compress na pud siya sa atong high pressure compressor. Then atan nang idong siya sa atong combustion chamber. Then once nga makaproduce siya og heat, then dong na pud siya sa turbine. So, mato ang atong intercooling. Here is the TS diagram of the intercooling. Kaning process 1, 2 is an adiabatic compression nga gikan sa katong ato ang kuan low pressure compressor. Then once nga iagi na siya sa ato ang intercooling is mo ubos ang iyahang temperature, then at the same time is ang iyahang entropy is mo ubos kay release man siya og heat. Then sa process 3 to 4 is atong high pressure compression. So sa process 4 is to 5 is kanya ang hot heat addition, which is atong combustion chamber at sa mo produce og heat. Then sa process 5 to 6S kani mo ni ato ang expansion, which is adiabatic expansion. Then kaning 6 to 1 is kanang heat rejection nato. Second method is the reheating. The output of gas turbine can be improved by expanding the gases in two stages with a reheater between the two. The high pressure turbine drives the compressor and the low pressure turbine provides useful power output. So man itong figure sa kaning reheating. So sa turbine ta mag-focus. So kani atong combustion chamber, then kani sa compressor. So agi na to sa combustion chamber. Then ang heat niya nga ma-release gikan sa combustion chamber is dong na to sa high pressure turbine. Then diba og mo kuwanta ni sa turbine is kanang mo ubos ang iyahang temperature. So ato siyang iagi og kuan kaning heat exchanger kaniya at reheat niya nato ani. Then atang isunod ari pasari sa atong low pressure turbine nga, which is kanang murag same lang siya og temperature sa kaning atong combustion chamber. TS diagram for closed loop cycle turbine. 1 to 2 is the compression kanina, Chabati compression. Then sa 2 to 3 is the heating gikan sa ato ang combustion chamber. Then ang 3 to 4 is the turbine expansion kani. So sa katong atong high pressure turbine. Excuse me. Then ang 4 to 5 is the reheater. So katong atong painit og balik. Ito balik ang atong air. Then sa 5 to 6 is the turbine expansion. So, ano to? Matoto ang reheating. Regeneration. The exhaust gases from the turbine carry a large quantity of heat with them since their temperature is far above the ambient temperature. They can be used to heat air coming from the compressor, thereby reducing the mass of fuel supplied in the combustion chamber. So kanito ang figure sa regeneration. Una is moagi sa air compressor, then agi sa combustion chamber, sa turbine, then ang exhaust gas nato gikan sa turbine is ato siyang ibalik ari sa kaninga part kani ang sa itong combustion chamber kay kung ano man siya. So ubos-ubos man niya temperature ani nga part kumpara sa atong exhaust gas. So ato siyang ang heat gikan sa atong exhaust gas is atong i-transfer ani nga part para itong ato sa combustion chamber. So mo to ang regeneration. Regenerative cycle has more efficiency than simple cycle at lower pressure ratio. The above certain pressure ratio limit the efficiency of cycle drops, since in that case regenerator will cool the compressed air instead of heating it. Sama to. Thank you.
Vapor cycles. So the Carnot vapor cycle 1 to 2 is isothermal heat addition in a boiler. So ang 1 to 2 is isothermal. Kasabot ana is init. Di ma-change ang heat. So munang boiler na. 2 to 3 is isentropic expansion in turbine. So yung tag-turbine, bali ang steam nagikan sa boiler, sumara sa turbine na, so manay produce o kuan. Kasi itong turbine, tuyok na. So mana tong output create sa electricity nga na tungod sa torque na hitabo. So 3 to 4 is isothermal heat rejection in the condenser. So bali ang steam nagikan sa turbine, no? Dong sa condenser na niya, may mo siyang water, pabugnawan niya ng heat rejection. So 4 to 1 is isentropic compression and compressor. So babalik na po siya sa boiler. So complete cycle na siya. Ngayon tanawon rin sa TS diagram, 1 to 2 is boiler na. So high temperature dyan sa muna sa mas babaw, no? Sa 2 to 3 ang steam sa turbine. So lang siya ubos, no? So sabutan na mo gamay ang temperature. 3 to 4, so pabugnaw na nato mo ng bilaw na dyan yung temperature. Pasaka na punta sa compressor. So manay cycle yan sa Carnot vapor cycle. So the Carnot cycle is the most efficient cycle, varying between two satisfied temperature limit, but it is not suitable model for our cycle because process 1 to 2 is the heat transfer process to two-phase systems severely limits the maximum temperature that can be used in the cycle. 374 Celsius for water. So process 2 to 3, the turbine cannot handle steam with a high moisture content because of the impingement of liquid droplets of the turbine blades, causing erosion and wear. So, tungod sa high moisture siya, ang mga liquid droplets mo sa turbine blades no niya mo na siya maka-create og usapon na siya mong maka-create og corrosion ana tumatayan. So process 421, so kani it's not practical to design a compressor that handle two pieces. So the cycle in B kani is not suitable since it is required isentropic compression to extremely high pressure and isothermal heat transfer at variable pressures. So yeah. Example number 1. A steady flow Carnot cycle uses water as the working fluid. Water changes from the saturated liquid to saturated vapor as the heat transferred to its form as a source at 280 degrees Celsius. So, mo na yung source no? So, mo na dito sa boiler. Heat rejection takes place at the pressure of 10 kPa or megapascal. Show the cycle on TS diagram relative to show saturation line and determine the thermal efficiency, the amount of heat rejected in kilojoules per kilogram, and the net work output. So bali nasa ko ano yung source sa heat 280 degrees na yung given of kaning heat rejection sa ating kPa. So non-cis condenser 3 to 4 1 to 4. So man ang TS diagram no. Ne. So bali 10 kPa na ni. Yeah. So nato diring ko 280 Celsius gikan sa high temperature. So T1 at T2 so equal to sila. So 10 kPa. So aron makuha na to yung temperature, magkwantanin sa steam table. At lang ni converting pressure to megapascal. So nani sa 0.01 megapascal. To between man siya sa 45 to 46 Celsius. Ang itong bot ito is interpolate para makuha na to temperature na 45.81 Celsius. So atong imong Kelvin so manang i-plusa na to 273. Manang nahimo sa 318.81 Kelvin. So manang atong ano T-low na to kaning T4 o T3 na to. So makuha na to atong thermal efficiency. So kaning equal to 1 minus T-low o T-high na to na temperature. So tayo substitute 1 minus 318.81 over 555. So ganitong T-high so manig dire sa itong given pa ni siya. Okay. The times ano na to ni Kelvin na 273 mo na 555. 53 na. So, may nakuha na to. So, ngayon na siya. 0.4235. So, times na to 100%. So, nakuha na to 42.35%. Ang itong thermal efficiency sa cycle. No? So, B, the amount of heat rejection. So, sabot na yung heat rejection sa itong may sa 3 to 4 na din sa condenser. Sa condenser no. So ma'am ni atong temperature sa atong T high so equal to 280 Celsius. So, mga value sa enthalpy na to. So, naraman na sa state table. Tanaw to evaporated enthalpy dito. So, maoning 1,543.2 kilojoules per kilogram. So, muna tong heat in, equal na sa atong evaporated enthalpy na. So, maning so, Q out equal na siya sa Qn times sa T log T high na to. So, manayag substitute niya, nakuha na nato na Q out equal to 889.67 kilojoules per kilogram. So, muna nga itong Q out mo, nag-reject sa atong nag-reject na heat. So, the network output. So, net equal man na sa Q heat na ingsod o heat na gawas. So, mapasabat na. So, man yan, substitute na ito mga value. So, makuha na ito ang work net na ito sa 653.753 kilojoules per kilogram. Nara, no? So, Rankine cycle, the ideal cycle for vapor-powered cycle. So, many of impracticalities associated with the Carnot cycle can be eliminated by superheating the steam in the boiler and condensing it completely in the condenser. So the cycle that results in a Rankine cycle, which is the ideal cycle for vapor power plant. The ideal Rankine cycle does not involve internal irreversibilities. 1 to 2 sa isentropic compression and pump. So, mana 1 to 2. Isentropic compression sa pump na gamit ani. So, 2 to 3 is a constant pressure heat added in a boiler. So, gikan sa pump, so there no, water, gihimo mo siyang vapor no, tungod sa or steam gikan sa giagi sa boiler. So, 3 to 4. So, sa isentropic expansion in turbine. So, steam dere sa gikan sa boiler nga sa turbine na para mag-create og torque na mga sa so produce ag atong work output na to. Electricity on sa torque na sa turbine na to. So, what na ang 4 to 1 sa constant pressure direction ng condenser. So, ang condenser na to, no? So, din ang heat out na to. Din ang heat out na to. Din reject ang heat. Siyang steam, gikan sa ginawa mo siyang water, no? Yung balik na mo sa pump. Siya ay complete cycle sa Rankine cycle. So, notes lang na to, only slight change in water temperature to pump. So, kita mo ito dito sa yung graph. So, 1 to 2, mga pump daw. So, gamay ra ang pag-change sa temperature. Gamay ra pag-change sa temperature. Gamay ra pagsaka niya. So, the steam generator consists of boiler, to process heat transfer and separator. So, turbine outlet is high quality steam. Condenser is cooled by water, like example, like lake, river, cooling tower, or by air. When water is scarce. So, thermal analysis of ideal Rankine cycle. So, the efficiency of power plant is in the US is often expressed in the term of heat rate, which is amount of heat supply in BTU to generated 1 kilowatts of electricity. So, may mga steady flow energy equation. So, heat in minus heat out plus work in minus heat out equals sa N sub E o N sub I. So pump na to is equal to heat equal to 0. So what yun heat ning pump no kay water man na. So equal to 0 na siya. Boiler so kasi water lang equal to 0 na siya. Turbine. Condensar pod. So work net equal na siya sa heat in minus heat out. So equal po na siya sa work out minus work in. So ang efficiency yan eh. No? So efficiency natin equal na siya sa work net over work in. Or equal po na siya sa 1 minus heat out over heat in. So the thermal efficiency can be interpreted as the ratio of the area closest by the cycle. At this diagram to the area under the heat addition process. No? Kumani nga formula na. Kung nasa pump in, work pump in, H2 minus H1, kami na to. So, pwede pa sa city minus pressure to sub 2 minus pressure 1. Ano? U in equal to H3 minus H2. So, U out ay work out H3 is 4. 8 out H4 minus H1. So, ano minus H4 minus H1 man na. So, tanaw na to dire. So, mamanig itong condenser dire. Mamanig manito mag heat rejection. So, manang H4 minus H1. No? Sa workout na to, sa turbine na wala ng H3 minus H4 na. No? Heat in na to. So, manang H2 minus H3. So, naman itong kwan dire. Para mo ito mag-add heat sa H2, H3, kaya naman drag boiler. No? So, pump in, nandiyan na sa H2 minus H1. Ayan. So, ideal regenerative bronchial cycle. So, it is transferred to the working fluid during process to the toe at a relatively low temperature. This lowers the average heat addition temperature and thus the cycle efficiency. In the steam power plant, steam is extracted from the turbine at the various points. This steam, which could have produced more work by expanding further in the turbine, is used to heat the feed water. Instead, the device where the feed water is heard by generation and called generator or feed water heater o FWH. So kaning sa generative rapid cycle na kuno siya iko kaning FWH kaning feed water heater. So a feed water heater is basically a heat exchanger which heat transferred from the steam to the feed water either by mixing the fluids or fluid streams or often feed water heaters without mixing the then close feed water heaters. So, nasa ido ka kon na open feed water heater o kon close feed water heater. So mo ni open feed water heaters. So the open or direct contact feed water heater is basically a mixing chamber where the steam extracted from the turbine mixed with the feed water existing the pump. So ideal the mixture leaves the heater as the saturated liquid at the heater pressure. So bali no nasa mani open feed water heater. So bali na sa ido ka pump dire pump 1 dire no mari sa 3 sa pump 2 So mudong sa boiler. Sa turbine na to. So ang steam nagikan sa turbine ari siya ko no. Balik siya daning open pan. Ano sila mag-mix sa feed water heater. So mix na po dan. So mabalik no steam. Yeah. So ang uban mudong ari sa condenser. So manay ko feed water heaters, open feed water heaters kay ang kuan dinit na water nga nagmixan sa water nagikan sa kuan turbine. So natin formula no, heat in is equal to H5 minus H4. So heat in, so ari man dyan na sa atong kuan no, boiler. So maning 5 minus 4. So it out na to 1 minus y times h7 minus h1. So naaray no sa atong turbine. It's out na to. So turbine padung ari sa atong condenser. Muna. So work output. Work turbine output. Ano siya kuan? Turbine na to. So h5 minus h6. So money. Plus ato ang 1 minus y o sa pwede mo na lang sa h6 minus 7. So ayan, maring kanin din yun muna itong work turbine output. So pump in, so muna itong pump, so y minus y times work pump in plus sa work pump datong number 2. So kanyo so closed feed water heaters, so another type of feed heaters frequently used in steam power plants in the closed feed water heater, so in which heat is transferred from the extracted steam to the feed water without any mixing taking place. The two steams now can be different pressure since they are not mixed. The ideal regenerative Rankine cycle at closed feeder heater. So kanina close ni. Gani closed feed water heaters. So nganong close kay patong tanawon ang dito sa open is boiler to turbine. So diri sila magmix sa kanang feed water heater, dinhi sila magmix. Ang water nagikan sa pump 1 o dire sa turbine mix sila. So usa sila modong sa pump 2. So mo to sa open. Pero dinhi sa close, man sang gitawag og close kay wa sila nagmix. Dinhi sa feed water heater. So tanawon niyo daron ang dinhi sa pump 1. So milap po siya dire sa mix chamber. So ang dire sa turbine sila po siya dire sa pump 2. So dinhi na sila nagmix sa mixing chamber o sa moari sa boiler no. Ano sa turbine. So muna ilang kalahian. Close kani wa nagmix sa closed feed water heaters. Na siya on mixing chamber. The closed feed water heaters are more complex because of the internal tubing network, and thus they are more expensive. So ang closed feed heaters daw is more complex siya, lisod siya tungkol sa yung internal tubing o mas mahal po siya. So heat transfer is closed feed water heaters is less effective since the two streams are not allowed to be directly contact. However, closed feed water heaters that not require a separate pump for each heaters since the extractive steam and the feed waters can be different pressures. Open feed water heaters are simple and inexpensive and have a good heat transfer characteristics. So, ang open daw, feed water heaters are simple daw siya niya. Di siya mahal. Ya, lami hindi po ko nagyan ko heat transfer characteristic niya. So, for each heater, however, a pump required to handle the feed water. So, most steam power plants use a combination of open and closed feeder heaters. So, kasagaran mo sa mga planta is kaning duha mo gigamit, no? Kaning open o closed feed water heaters. Kita man nato, no? Kani. Second law analysis of vapor power cycles. The second law analysis irreversibilities external to the steam, such as heat transfer through a finite temperature difference of the cycle reveals where the largest irreversibilities occur and what their magnitudes are. Energy destruction for a steady flow system. So, a second law analysis of vapor-powered cycles reveals where the largest irreversibility occurs and where start to improve. So, second law nung nag-isod na siya so dapit ang mga irreversibilities o asa po niya siya nag-start so sa pag-improve. Many industries require energy input in the form of heat called process heat. Process heat is in these industries is usually supplied by steam at 5 to 7 atm and 150 to 200 degrees Celsius. Energy is usually transferred to the steam by burning oil, natural gas, or another fuel in a furnace. Industries that use large amount of the process heat also consume a large amount of electricity power. So it makes sense to use the already existing work potential to produce power instead of letting it go to waste. So the result is a plant that produces electricity while meeting the process heat requirements of certain industries process. So cogeneration plant. Cogeneration, the production of more than one useful form of energy, such as process heat and electric power for the same energy source. So tayo pamula na utilization factor equal na siya sa power output plus power heat deliver over total heat input. So, equal po siya sa work net plus heat sub P o QN na to. So the utilization factor of the ideal steam turbine cogeneration plant is 100%. So actual cogeneration plant have utilization factor as high as 80%. No? Some recent cogeneration plant have even higher utilization factors. At times of high demand for process heat, all the steam is routed to the process heating units and none of the condensers M7 equal to 0. So the waste heat is 0 in this mode. Why ma-waste na heat? If this is not sufficient, some steam leaving the boiler is throttled by expansion and pressure reducing valve or PRV to extraction pressure of P6 and it directly to the process heating unit. So nasa ko ano expansion or pressure reducing valve sa heating process. So maximum process heating is realized when all the steam leaving the boiler passes through the PRB or Epsom pipe equal to input. So number power is produced in this mode. When there is no demand for for process heat, all the steam passes through the turbine and the condenser. So 5 equal to M6 equal to 0. So the cogeneration plant operates as a ordinary steam power plant. So nato yung mga equation, no? So Qn equal na siya sa M sub 3 times H4 minus H3. So mo na itong sa boiler na to, no? So Q-out na to, sa Q-out sa ito mo ng condenser, so mo ng M sub 7 times H7 minus H1. So Q sub P na to, so times sa ano, M sub 5 times H5 plus M sub 6 times H sub 6 minus M sub 8. So times sa 1 H sub 8 niya. So work sa turbine na to, so mo ng H sub 4, M sub 4 minus H sub 5. So times na siya sa H sub 4 minus H sub 6 plus M sub 7 times H sub 6 minus H 7. So confined gas vapor cycles the continued quest for higher thermal efficiencies have resulted in rather innovative modification to the conventional power plants. Popular modification involves a gas power cycle tapping a vapor power cycle. So, combination is ako na sa gas power cycle o vapor power cycle. So, which is called the combined gas vapor cycle or such the combined cycle. So, the combined cycle is the gas turbine from Britain cycle tapping with the steam turbine. So, current kind cycle. So, it has higher thermal efficiency than either of the cycle executed individually. So, it makes engineering sense to take advantage of the very desirable characteristic of the gas turbine cycle at the high temperatures and to use the high temperature exhaust gases as the energy source for the bottoming cycle, such steam power plant. So the recent developments in gas turbine technology have made the combined gas steam cycle economically very attractive. Many new power plants operate combined cycles, and many more existing steam or gas turbine plants are being converted to combined cycle power plants. The thermal efficiency is over 50% as reported. So, combined gas steam power plant. So, bali, kanina sa babaw, so muna itong gas cycle. So, kanina boss is ang steam cycle na to. So, ang steam, so mamanig ko sa steam. So, pump. So, wala siya ko, no? Wala siya ko, no? Wala siya boiler. So, bali, ang exhaust nagikan sa sa turbine dito sa combustion chamber. So, muna magpa-heat sa sa water. So, ang steam, hindi ka na so, muna yung makakuan sa itong turbine. Tuyok din sa itong steam cycle. So, aras condenser, So, di na siya magamit og boiler. Kaya na siya heat exchanger na sa exhaust gas nagikan sa atong turbine gas. sa atong kuan sa gas cycle na to. So mo ni pressure so ang air so nasa combustion chamber. So gas cycle ni combustion chamber so ara sa turbine ano move so atong output ano ni atong output no? Kita electricity nga na so mari sa heat exchanger. So ang heat exchanger mo po yung painit sa atong water. So mo nang gihita so natay steam turbine. So mas efficient na siya. I-combine ang duha ka kuan cycle. So maora to.
So let's tackle about the advantages and disadvantages of the combined cycle power plant. So the advantages is the efficiency of the combined cycle power plant is better or higher than the turbine cycle or steam cycle power plant, fewer moving parts and less vibration than reciprocating engine, very low toxic emissions, runs on a wide variety of fuels, and high operating speed. While in disadvantages, the higher cost, longer startup, less responsive to power demands, and shrill whining noise. That are the advantages and disadvantages of the combined cycle power plant. So, advance in turbine technology, the TIAC system. So, TIAC means turbine inlet air cooling system. So, this TIAC technology has gained immense popularity over the last few years, especially in normally hot regions. Cooling inlet air, which is the core function of TIAC systems, increases total mass flow rate, thereby enhancing power performance of a gas turbine. By cooling the inlet air, the power output of the gas turbine can be boosted up to 20% or 30%, while the efficiency is increased around 3 to 5%. Thanks to these good benefits, combined with low capital cost, turbine cooling is a very popular technology for existing and new gas turbines. So, this is the actual and diagram of a TIAC system. A gas turbine is a unit that comprises of an expansion turbine, a compressor, and a combustion chamber. Compressor design is critical since the thermodynamics efficiency of this unit depends on temperature and pressure drop of the air. Manufacturers can optimize compressor design such that the pressure at turbine inlet is high. We can already see this improvement in frame H gas turbines, specifically having around 23:1 pressure ratio. For gas turbines, higher compression ratio translates into higher efficiency. Obviously, this has an implication on the fuel gas pressure, which must now increase. There are gas compressors to help achieve these pressures. The common types include centrifugal, reciprocating, and screw compressors. So this is the first power plant in the US, the Long Ridge Energy Terminal. So this is purpose-built for generating power with hydrogen fuel. And this is the Mitsubishi Power's H25 series gas turbines. It is a heavy-duty type that can achieve high efficiency with heat recovery steam generators as cogeneration system or combined cycle power plant. Another way of increasing gas turbine performance is by increasing sensible heat. This is exactly what this advance does. It can extract feed water from HSRG and direct it to the heat exchanger. With the shell side containing natural gas and the tube side containing a hot feed water, natural gas temperature rises significantly. Consequently, combustion efficiency increases. The cool feed water will then recirculate back to the HRSG preheater condensate line. A number of criteria are followed when designing this advanced system. First, in case of heat exchanger leak, early warning to prevent failure and infiltration into combustion system. Next, prevent infiltration of feed water system by gas fuel, and protect system piping and components from overpressure. So, this is the Environmental Impact Statement report submitted by Excellent Energy Resources Incorporated. It is the proposed 1,700 megawatts Batangas Combined Cycle Power Plant project. So, this is the vicinity map of the proposed 1,700 megawatts Batangas Combined Cycle Power Plant project. So, pollution control devices. One of these is the wastewater treatment system. The wastewater treatment system, including sanitary treatment system, will collect and process the wastewater, sanitary waste from the entire plant, and auxiliary facilities to meet the criterion of wastewater discharge based on the standard and environmental regulations. So, the wastewater treatment system, including sanitary treatment system, will receive and process all contaminated water, including but not limited to wastewater from the following sources. So, contaminated effluents from boiler drains and blowdown, from floor drains of boiler area, and from the turbine drains of turbine area. And next is oily effluents from transform area, fuel oil tanks and pump house, lube oil tanks, workshops, and etc. Sanitary wastewater from the buildings, sludge blowdown from the sea water clarification, chemical wastewater from water treatment system. So, collected contaminated water will be treated through wastewater treatment system and stored at effluent pond before reuse or discharge to the sea. Potentially, oil-contaminated wastewater from the power plant will be routed through an oil-water separator and then sent to the normal wastewater pond for treatment as necessary. Sanitary waste will be collected separately from the other wastewater. This sanitary waste will be treated in a packaged sanitary waste system with provision for manual grab sampling prior to being discharged to the sea. The wastewater treatment system will consist of the following major components: normal wastewater pond, abnormal wastewater pond, neutralization pond, WWT clarifier, WWT granular media filter if necessary, treated wastewater pond, thickener, dehydrator, API oil separator, oily wastewater pond, CPI oil separator, skim oil pond, and chemical ejection facilities for WWT. So, the sanitary treatment system will consist of the following major components. Sanitary treatment package. Treated wastewater will be used for the service water as much as possible and also discharged to the seawater outfall. Continuous emission monitoring system. So, it will be installed on each boiler units with real-time display monitoring system. The CEMS consists of a standalone electronic analyzer designed to measure CO2, CO, NOx, SO2, O2, and VOC. CEMS will be mounted on flue duct between ID fan and the stack or on the stack for emission monitoring. An alarm device is integrated in the system in case standards are exceeded. This data will be integrated in the plant DCES by input-output interface. So the CEMS shall compose of O2, NOx, CO analyzer, opacity meter, analyzer cabinet, and sampling line. So this is the gas turbine power plant, or the Brighton cycle. So atmospheric air is continuously drawn into the compressor where it is compressed to a high pressure. The air then enters the combustor where it is mixed with fuel and combustion chamber. The combustion product expand through the turbine and are subsequently discharged to the surrounding. Next is the steam or vapor power plant, or the Rankine cycle. So the 1 to 2 turbine isentropic expansion of the working fluid through the turbine from saturated or superheated vapor at state 1 to the condenser pressure. 2 to 3 consider condenser isobaric heat rejection. Heat transfer from the working fluid as it flows at constant pressure through the condenser with saturated liquid at state 3. Three to 4 pump isentropic compression. Isentropic compression in the pump to state 4 in the compressed liquid region. Then 4 to 1 boiler isobaric heat addition. Heat transfer to the working fluid as it flows at constant pressure through the boiler to complete the cycle. Now, both of these cycles can be combined together, and the reason for that is that when we look at these two cycles separately, they operate at certain temperatures. So the gas turbine power plant, usually the topping cycle, because it operates at a higher temperature. And steam turbine plant that is operating on the base of Rankine cycle because of its operating temperature being lower, especially across the condenser. Then these are usually the bottoming cycles. So the gas and vapor power plant are combined using an interconnecting heat recovery steam generator that serve as the boiler for the vapor power cycle. The combined cycle has the gas turbine's high average temperature of heat addition and the vapor cycle's low average temperature of heat rejection, and thus a thermal efficiency greater than either cycle would have individually. We can calculate the efficiency for this combined cycle by net work done across the gas cycle added to the net work done across the vapor cycle divided by the heat content that is being supplied.
So now we're going to solve this problem. The gas turbine portion of a combined gas steam power plant has a pressure ratio of 16. Air enters the compressor at 250 Kelvin at a rate of 12 kilograms per second and is heated to 1400 Kelvin in the combustion chamber. The combustion gases leaving the gas turbine are used to heat the steam to 450 degrees Celsius at 10 MPa in a heat exchanger. The combustion gases leave the heat exchanger at 400 Kelvin. The steam leaving the turbine is condensed at 10 kPa. Assuming all compression and expansion processes to be isentropic, determine A. the mass flow rate of the steam, B. the net power output, and C. the thermal efficiency of the combined cycle. For air, assume the constant specific heat heats at room temperature. So, ang ma-involve na cycle na to ani is ang Rankine cycle o ang Brighton cycle. So kani nga ubos nga portion sa ato ang graph sa TS diagram na to ani is our Rankine cycle, or what we call as steam cycle. And of course kaning ato ang ani mo na itong gitawag og Brighton cycle or ang itong gas cycle. Karon let us identify the given. So na ko na siya combined gas steam power plant na naay pressure ratio of 16. So let's write our given. Pressure ratio, let's set as PR, 16. Air enters the compressor at 250 Kelvin. So, ang atong compressor na side, aron tanawon nga ato ang diagram ani is here. So, this is our compressor. So, i-enter ang air sa compressor at 250 Kelvin. So, that will be our T5. By the way, naka-Kelvin ito ang temperature. So, we have 250 at a rate of, so natay kanang mass flow rate na 12 kilograms per second. 12 kilograms per second. And is heated to 1400 Kelvin in the combustion chamber. So, sa combustion chamber na to, kari, ano yung combustion chamber na to? So, gipaiit ang kanang air na nisod sa combustion chamber to 1400 Kelvin. So, asa na nilapit? So, naani siya sa aning paggawas niya sa nasa 7 lapit. So, at T7 na siya 1400 Kelvin. The combustion gases leaving the gas turbine are used to heat the steam to 450 degrees Celsius. So, init siya to 450 degrees Celsius at 10 MPa in the heat exchanger. So, ato madapit atong heat exchanger kani. So, ang atong heat exchanger, ni-mention na sa ganiha, na it is also called as ato ang HRSG or the heat recovery steam generator. So, nada siya sa 10 MPa. So, ani 10 MPa. The combustion gases leave the heat exchanger at 400 Kelvin. So, leave siya at 400 Kelvin. Ato lang to. Tanawon sa ato ang diagram. So, we have gawa siya sa exchanger at 400 Kelvin. So, kaning 0.9 na to. Wala siya 400 Kelvin na. Ano ito gamayari? This will be your steam cycle. Okay, the steam leaving the turbine is condensed at 10 kPa. So, the steam leaving the turbine, so aning paggawas niya sa steam turbine, aning nga point sa P4. So, na siya 10 kPa. Assuming all the compression and expansion processes to be asymptotic. Asymptotic meaning reversible and adiabatic. So, meaning ang imong entropy is constant. So, this is, for example, sa constant entropy is ang process T4 2165 o 72 niya. Kung asymptotic ni pod, your Q is equal to 0. So, meaning y heat transfer nitabo. For air, assume the constant specific heat at room temperature. So, also na itong specific heat sa air. So, your specific heat at constant pressure sa air is 1.005 kilojoules per kilogram Kelvin. By the way, ang ato ang reference nga book ani is katong thermodynamics, an engineering approach by katong Sinjel nga libro. Okay. We also have napatay ko katong ratio, which is gitawag siya K ratio sa CP over CV. Specific heat ratio, which is approximately 1.4. So, ang atong ipangita niya is ang mass flow rate sa steam, and the net power output and the thermal efficiency. So, ano ito pagpangita sa mass flow rate sa steam? So, we know that naatay sa atong balik sa ato ang sa graph. So, we know that na ini-enter ani nga heat Q in na siya sa imuhang combustion chamber. And this part, process 6 to 5. And process 6 to 5 is our compressor. So, naasay chay compressor ni work in sa compressor sa gas cycle, and then kinisad na siya work out sa gas turbine. And same sila ni na siya pani nga process. 4 to 1 is our condenser na side. So naay ni gawas ani Q dot out, which is ang compressor, I mean condenser. Q dot out is natin na Q dot out, and then kainsad na siya nga process 1 2 na siya work na produce ani sa pump here, process 1 2. So work dot in sa pump, and then ang process 3 4 is ang kani sa steam turbine. So naa siya work out dot out sa turbine, kani sa turbine sa gas, kani po siya sa steam. Okay, so pangitaon na to na ang value sa Qn. So di ba natin formula? So muna ni solution. So natin Q dot in is equal to the mass flow rate sa air times delta H, which is sa kani H7 minus H6. H7 minus H6. Di ba nabot tayo formula nga M dot sa air times Cp times T7 minus T6. Karon naa naman tayo T7, which is given ganiha nga 1,500 Kelvin. At pangitaon na to ang temperature sa 6. Solve T6. So in solving T6 natay ratio nga T6 over T5, which is equal to P6 over P5 to the power of K minus 1 over K. So solving for T6, so T6 is equal to T5, so kapiyon na P6 over P5 times K to the power of K minus 1 over K. So substituting values, natin T5 kanino 250 Kelvin. So we have 250 so tatapkon minutes to 250 Kelvin over P6 is okay. Natay ratio nga 16. So yung pasabot nga ratio nga 16. So meaning imuhang pressure ratio is equal to the pressure sa P6 over P5, which is equal to 16. Yung isa-substitute nandito na ito ng 16 ani. 16 to the power of 1.4 minus 1 over 1. Okay, T6 is equal to 552.04 Kelvin. So karon substituting ani nga formula, makakita na ta sa Qn. Okay, let's substitute Qn. Q dot in is equal to mass flow rate sa air is 12. So you have 12 kilograms per second times 1. Specific heat 1.005. Units niya is kilojoules per kilogram Kelvin times T7 mo 1,400 minus 552.04 Kelvin. Okay, so your Q in, let's do this another color. Q dot in is equal to 10,226.40 kilowatts. Okay, kaya cancel naman siya, cancel. So kilojoules per second is kilowatts. Next, By the way, mo ni siya sa sa let's say this, gas cycle na siya. Gas cycle. Okay. Now for the compressor work, let us solve for the compressor work. So solving for the compressor work aside of the compressor. So solving for the compressor work, we have the formula. Work dot C is equals to mass flow rate sa air, Cp times T6 minus T5. So substitute na dito. Kailangan tayo given na ni. So you have 12 kilograms per second times 1.005 kilojoules per kilogram times Kelvin times 36, nagtapa 36, 552.04 minus 35 is 250. Okay, 250 Kelvin. Work dot C is equal to 3,642.60 kilowatts. Okay. So muna to ang work dot out. Oh, yes, work dot out sa turbine. So to solve this, we have turbine work. So work dot sa turbine is equal to m dot sa air mas flow rate sa air magyapon Cp times karon T7 kay kuan man turbine man T7 minus T8. So substituting na kay na naman sila mga formula W dot T equal to 12 kilograms per second times 1.005 kilojoules per kilogram times Kelvin times 1,400 minus 600. Tama ba? 1,400 minus your T. Oh, by the way, what by T8, no? 188. So solving for T8. Let us solve for T8. So solving for T8. Solving for T8. P7 over T8, which is equal to P7 over P8. Power of K minus 1 over K. So T7, substituting values dito na, no? 1,400 over T8, which is equal to P7 over P8 is our pressure ratio, 16. So you have 16, 1.4 minus 1 over 1.4. So I should solve na to na T8 is equal to 634. 634 Kelvin. Okay. So now substituting balik sa work sa pump. Work sa pump sa turbine. So they have 12 kilograms per second times 1.005 kilojoules per kilogram times Kelvin times 1,400 minus 634 Kelvin. So you have again work dot sa turbine is 9,237.96 kilowatts. Now, na naman tayo work sa turbine, na naman tayo work sa compressor. Pwede na ito ma-solve ag work net sa gas cycle. So saan man? So simple ra. Ang work net sa gas cycle, work.net sa gas cycle is work dot sa turbine na sa gas niya. So na to net sa gas. So work dot net sa turbine minus work dot sa compressor. Work dot sa turbine minus work dot sa compressor. So sa turbine, you have 9,237.96 kilowatts minus, so compressor nimo is 642.36 kilowatts. So ang work dot net sa gas is 5,595.36 kilowatts. 36 kilowatts. Okay. Since napamatay mga missing na kuha ani, like kaning H1 na to, H2 matakabaw sa mga enthalpy niya sa ani ta sa steam cycle. So karon solve na to mga enthalpy nila. So ato ta sa steam cycle. Steam cycle. So at state 1, state 1 okay, so at state 1 we have P1, which is 10 kPa. So kanina 10 kPa, makita na to ni siya sa table kani siya, table A5 page 890. So makita na to nga sa state 1 naman siya sa saturated liquid line. So kanina mo ni saturated liquid line to, di ba? So nasa siya sa saturated liquid line. Iyang entropy ana is 191 kani 191.81. So iso na to. Your H1 is 191.81 kilojoules per kilogram, and then your specific volume ang part is V1 is equal to 0.001010 cubic meter per kilogram. Now, solving for state 2 at state 2. So, pressure sa state 2 is nasa 10 MPa. So, P2 is equal to 10 MPa. So, sa may sulit na. So, to solve for H2, you have H2 plus H2 is equal to H1 plus B1 times P2 minus P1. Okay? So, H2 is equal to H1 na 191.81. Hindi na isuot ang units para libog. Plus V1 mo is 0.001010 times P2 mo is 10 MPa, that's 10,000 kilopascal. So minus P1 mo is 10 kilopascal. Minus 10. So your H2 is equal to 201.90 kilojoules per kilogram. Now solving for state 3. Okay. Solving for state 3. At state 3, so you have P3. P3 is equal to same na po, nalagapon siya sa 10 MPa. 10 MPa. So H3 is, tanawin sa ito sa table, check na ito. 10,000. Nasa sa superheated, kanina saturated, saturated water. superheated. So again, ang pag-solve sa ato ang H3 is na we know nga naatay kanang temperature nga 450 sa heat exchanger na to. So sa 450 nga temperature sa 10 MPa nga pressure, ang ato ang enthalpy is 3,242 na kay 3,242.4 kilojoules per kilogram. So muna na to ang H3. We know that ang H3 na to is entropy sa H3 is equal sa entropy sa H4. So ito na isulat S3 is equal to S4. So atong S3 is 6.4219 kilojoules per kilogram Kelvin. Now solving for state 4. At state 4, you have P4 is equal to 10 kPa. So tanaw na to ang state 4 na to, no? Kay nasa siya sa sud sa ani nga curve, which is ang sud ani nga curve is vapor. So pangitaw lang to na ang iyang moisture content, mamatali ng X. So X4 is equal to S, ang formula is X sub 4 is equal to S sub 4 minus SF over SFG. So balik ta, asa na ito makita ni mga values sa SF o sa SFG. So ano na siya makita sa table A5 sa ato gyapon sa 10 kPa na pressure under sa evaporation ang SFG o saturated vapor ang SF. So plug in na dito. Plug in na dito sa values. So ang atong SF4 is 6 S3 is equal to S1 man kaya in isentropic constant entropy constant entropy. So 6 minus 6.4219 minus SF is 0.6492 maklaro ba? Okay. Over SFG is 7.4996. So ito X4 is 0.76973. And to solve for HF4, you have to solve for H4 is you have enthalpy sa 4 is equal to HF plus X HFG. So, asa ito makita na, nalagyan na rin sa enthalpy. So, HF nimo is 191.81 plus X 0.76973, and then HFG is 2392.1. So, hindi na ito isuot ang units kundi madugay. So, H4 is 22,033.08 kilojoules per kilogram. Now we can solve the mass flow rate of the steam. So energy balance na. So E dot in is equal to energy dot out. So ang atong energy is diba summation na siya. Summation sa mass times enthalpy. Summation sa atong E is summation sa M dot sa mass o sa enthalpy na ni-enter sa system, which is equal to the mass na ni exit times enthalpy na ni exit sa atong system. So you have M ms H3 minus H2 H3 minus H2 sa dapit sa heat exchanger. Dapit is equal to sa steam ni siya, ms no? Sa ms sa mass sa steam is equal to mass sa air H so na siya H8 minus H9. So mali ang mass and mass balance or energy balance sa heat exchanger. So H8 minus H9. So di ba kani siya kay equal naman na siya sa dati na siya no? Okay, ano flow rate man. So kani siya is equal siya sa m dot air specific heat times T8 minus T9. Okay. So mass sa air now, mass sa steam. Now masolve na to, that is m dot sa air C specific heat times T8 minus T9 over H3 minus H2. Substituting values na dayon. So you have say 12 is kilograms per second times 1.005 kilojoules per kilogram times Kelvin. So ito pong units kaya makabata kasi ito ang makansel o dili. So T8 na to is 634 minus T9 is 400 Kelvin. Kelvin over H3 na to is 3242.4 minus 201.90 kilojoules per kilogram. Na makancel si kilojoules and then makancel si Kelvin, cancel sa kilogram ani. So what will is kilogram per second, which is m dot s is equal to sa steam 0.928 kilograms per second. So letter B, proceeding is letter B. Letter B is to solve for B, net power output. So net power output niya sa kani kinasolve na naman ang gas na. So ato na lang isolve ang steam. So sa steam work dot sa turbine, ito sa turbine sa steam, which is equal to m dot s h sa turbine h3 minus h4 h3 minus h4. Okay, so natin mass flow na 0.928 kilo or 0.928 dito na yun. H3 na to is solve naman to itong H3 and H4 dito naman ako 3242.4 minus 2033.08 naman to ari H3 bara na H4 kare. So ang ato ang work dot sa steam turbine is 1122.25 kilowatts. So work sa pump sa steam na gyapon ni siya m dot s times work work sa ito, some sort sa pump. So 0.928 times sunod mo na siya sa 10.0899. So you have 9.36 kilowatts. That's a pump. By the way, gilitso lang siya. So ang proper di ani is ang pag-solve sa work sa pump katong iyang specific volume na 0.001010 times sa change in katong pressure niya nga 10,000 kPa minus 10. So manang answer og 9.36. Next is ma-solve na to ang work dot sa net sa steam. So that is 1,122.25 kilowatts minus 9.36. So answer would be work dot net sa steam is 1,112.89 kilowatts. Sa steam na siya. So karon ato ang solbo na ang work net or yes, the net power output sa combined cycle. So you have work dot net is equal to 5,595 5,595.36 plus 1,112.89 kilowatts. So your answer is work dot net is equal to 6,708.25 kilowatts. Now solving for letter C. So lastly, we have C, which is so ito pangalan sa C is enthalpy. Enthalpy. C, ang pangalan sa C is thermal efficiency of the combined cycle. So ang thermal efficiency niya, ang formula sa thermal efficiency is thermal efficiency sa combined cycle is equal to the work done or work net over Q in. So substituting value 6,708.25 over solve tong Q in ganiha, which is 10,226.40 times 100%. So you have a thermal efficiency of 65.597%. So dako na kayo ang thermal efficiency ani. So that would be all. Thank you.